So in other words, if I gave you a point in one image of a calibrated set of cameras, there's a line in the other image that that point must lie on. What's that line called? That's the epipolar line. But notice that everything on this side of the slide is algebra, right? Forget all the geometry stuff. So what we've done is we've now converted the epipolar constraint into an algebraic expression. Thank you very much. No, that's what we're going to use. Okay, great. All right, so you ready? This is actually a good quiz. You know why? Because the quiz is going to make us do some work. So that was fine what I just showed you for some converged cameras. What about if the image planes are parallel? What happens? A, well, that's a degenerate case, and we're going to see that in just a minute. B, that's fine, it's no problem. It just means that R is the identity matrix, and the math just works. C, I have no idea. Okay, that's usually a bad answer to put on a final just saying. By the way, and so C is not the answer. I have some idea. So the answer to the rotation matrix is just the identity. So let's work through this a little bit. Let's do the essential matrix computation for the example of parallel cameras. Okay? So first, what is, so by the way, you recognize this picture? Right? This is the picture of our parallel image planes when we were doing the stereo, the derivation of the relationship between disparity and depth. So I have two parallel image planes. Nothing is rotated. Oh, nothing is rotated, so what's the rotation matrix? Well, it's just the identity. Great. All right, what's T? Well, what was T? T was the translation between the two camera centers. Well, in the geometry that we've defined here, the camera center has just been translated an amount b in the x direction or negative b in the other x direction. Doesn't matter, but we'll just say it's minus b, 0, 0. Okay? So T is just minus b. All right? Well, that means I can now compute my essential matrix, because my essential matrix, defined before, was this weird cross product thing of T times R. R is the identity, so we just plug T into the cross product little formula I gave you, and it looks like that. So that's our essential matrix. Let's make use of that matrix. All right? What does the essential matrix constraint say? The essential matrix constraint says that P prime times E times P equals 0, right? Where P prime and P are the location of the points, one in the prime frame and one in the regular frame. All right? So where are our points P? Well, it's in some location cap X, cap Y, cap Z, okay? Which is also, in the other frame, cap X prime, cap Y prime, also Z, because the Z's are the same because our planes are parallel, right? Right. So here are our points written. And the first time I wrote them as we said before. P is X, Y, Z. P prime is X prime, Y prime, and the same Z. But kind of written kind of cool over here, right? We assume that under normal projection, little x is F times big X over big Z. So I'm just writing big X as Z times little x divided by F, okay? And that's how I entered in these things here. Same thing with the primes over there, okay? Let's put those points in our essential matrix equation, all right? So I just inserted them here using our E, and now I've done something a little bit sneaky again. So here I have P prime, E, P. But you'll notice I've now divided my points all the way through by the amount Z over F, a constant, right? Z is whatever, I don't know what the value is, but it's some constant value. And F, might not know what that is, or I might, some value. And I just divided all the points through by that. Now, why am I allowed to do that? See, in class, everybody yell out the answer. But over the ether, you guys can say, because it equals 0, dummy. All right, so I can multiply anything I want by a constant and it stays equal to 0. And I just wrote it this way to make it easier to see the equations that are about to happen. So I just divided by Z over F. Copy that equation over again. Multiply out the first one. So now we have X prime, Y prime, F dotted with or transpose of 0 BF minus BY equals 0. Multiply it more again. We get BFY prime equals BFY. B is a constant, F is a constant, divide through, and it just says Y equals Y prime. Y equals Y prime. What does that mean? Oh, that means if I have some point in the image at location xy in the regular frame, the line y prime equals y is the line that this point has to be on. And think about what this is. So a point's at xy, so it's at some x location and it's y. Let's suppose y is 17. The equation y prime equals 17 is what? That's a horizontal line at height 17. So what this says is our epipolar constraint for parallel cameras, right, is that given a point in the image, the corresponding point is on the same horizontal line. Except last time, I just had to make you believe me. In fact, you didn't even ask the question, because it's very quiet in here. But it made common sense that if these cameras were lined up, it should be at the same line. Well, common sense doesn't get you very far in mathematics. Here is the derivation, if you will, that from parallel planes, you can, lined up this way, that your epipolar lines are horizontal. Okay? So the answer to that previous quiz of does this work for parallel planes, it works beautifully, actually. The rotation matrix is just the identity, and it derives out that your epipolar lines are, in this case, the parallel horizontal lines at the same height. Cool, huh? Okay, so that's called the essential matrix, and it's maps between calibrated systems. And what was really important about this whole operation is that we converted the geometric constraint that we had talked about back in the stereo days when we were talking about epipolar planes and looking for them. We converted a geometric constraint into an algebraic constraint. All right. But you ask, suppose I have uncalibrated cameras. Geometrically, thinking about it, if you gave me enough points that you told me this point corresponded to that and this point corresponded to that, it feels like I should be able to figure out how the epipolar lines are constrained. So what I need to do is to somehow figure out the algebraic relation between images given those correspondences, and that algebraic relation will give us a relation between a point in one image and its epipolar line in the other image if you gave me enough correspondences. That's what's called the fundamental matrix, and that's what we'll do in the next lesson. Welcome back to Introduction to Computer Vision. Today we're going to wrap up our unit on essentially calibration in stereo. We're going to talk about the fundamental matrix. Last time we developed the relationship between two views of two calibrated cameras where I actually knew the rotation and translation between them. And what was cool is we essentially went from what the geometric constraint was, that whole epipolar constraint that we had shown very early on, and we derived from the geometric constraint an algebraic constraint. And in particular, we defined something called the essential matrix, which related between two views, or I should say world points of two calibrated cameras. So the same point in the scene, the two different views of it, what the relationship was between them. But you might ask, suppose I don't have a calibrated camera. All right, well look, let's think about the intuition. If you gave me two images, and you gave me enough points to tell me that this point is this one, this one, this one, this one, gave me enough corresponding pairs, it feels like you should be able to figure out, say, the epipolar lines, that is how the lines map across, and what the correspondence should be for all the other points. And when I say correspondence, where they can be along the epipolar line depending upon their depth. Well, today what we're going to do is we're going to make that intuition real. We'll do the mathematics of this relationship between two uncalibrated points. Let's talk about, I'm going to call it weak calibration. And what I mean by that is we're just assuming that we've got two projective cameras so that they're going to behave like projected cameras. But in particular, we don't know anything about focal length or their offsets. But we are going to assume, for example, that we don't have radial distortion. We're going to assume that we don't have a non-uniform stretch of the image. But when it's, say, weakly calibrated, that's all we mean. We correct for that. So the main idea is that we're going to estimate the epipolar geometry from a set of corresponding points between uncalibrated camera images. And we'll probably use a large set, so it's going to be somewhat redundant in order to make this thing more robust with respect to noise. All right, so let's get started. So before, from all our projection stuff, you'll remember that we had this projection that went from a world coordinate through our extrinsics to our intrinsics to a projective representation of the image coordinate, right? And so to get the non-homogeneous, you had to divide through. So it's written here like it's a scale, W times the image point is equal to the world point times our extrinsics times our intrinsics. So phi is just as we did before. We're going to use a 3x4 version here since K will be a 3x3, where the left-hand side is that rotation matrix and the right-hand side is the transformed translation. And you'll notice a slightly weird form written here of it's R times T. And all that's saying is that if you know the translation in one frame, you might have to translate, you might have to express it in the other frame depending exactly on how you're doing this. Don't worry about that detail. Okay? So that's phi, our extrinsic parameter matrix. And K, if you remember, that's our intrinsic calibration matrix. And the K that I'm showing you here has a focal length and an X scale and a Y scale. And of course, as we said before, they're multiplied together. You really only need two numbers. You've got F divided by Sx and F divided by Sy, so they always appear as multiples like that. But we have a scale in both directions. We have the offsets, but what we don't have is we don't have any skew. That is that this value here is 0. That makes this math a little bit easier, and as I said before, in general, for modern cameras, skew just isn't an issue. All right, so I'm going to write that this way. The point in the image, and this is a homogeneous point, is a point in the world times our multiplied by the extrinsic matrix multiplied by the intrinsic matrix. But this, of course, is just the world point put through the extrinsics. That is the location of the point. It's a 3D point, but it's in the camera frame. Remember that the extrinsic matrix maps us from some arbitrary world frame into the 3D frame of the camera. Okay, so that we're going to call that PC. And so we can write down this very simple relationship that K, the intrinsics here, maps us from the point in the camera coordinate system to the homogeneous point in the image. Okay, so P in the image is equal to K intrinsics times P in the world. It's the point in the world, but expressed in the camera frame. Now, this is as if I had phi and I had K, etc., but I said that this was uncalibrated, right? Right. So let's suppose we have a given camera, Pm equals K times PC. All right? Now, see that K? That K intrinsics, that's a nice, assuming we don't have zeros sprinkled through here on the diagonal, that's a nice invertible matrix. So I can invert that K, and that's what's shown here. Okay? And what this says is that I can go from the image back to the point out in the camera frame. Now this should bother you a little bit, just a little bit, because it says this equation's fine, okay? We derived this a long time ago. We said if you gave me the 3D point in the camera's frame, I knew where it landed in the image. But this second equation is saying that I can go backwards. You can tell me where I am in the image, and I'll be able to tell you where I am in the world. And that seems wrong because that whole projection operator. And then you say, aha, this is not a regular 3D point, this is a homogeneous point. And you remember the projective geometry stuff we did a couple times ago? That's anywhere along the ray. And that's correct, right? If you tell me where I am in the image, if you just tell me the basic camera intrinsic geometry, I now know the ray in space that point came from. And that's all the projective geometry, the homogeneous coordinate is telling me. That if you give me the point in the image and the intrinsics, I can tell you the ray in space, which is the same as a homogeneous the homogeneous coordinate in the image. Okay? That's why we can go from an image to what feels like a world point, but is really just the ray. So now I can take that equation, and I can say, well, suppose I've got two cameras, typically called the left one and the right one, or the up one and the down one, or the forward one and the back, or just the main and the prime. Two cameras, okay? Here written left and right to be convenient, okay? Now, we have a different internal calibration matrix per camera, right? The two cameras may be the same kind of lens, same everything, or they may be quite different. All I need to think about is that there exists an intrinsic calibration matrix for each one. And by the way, this is uncalibrated, right?